All right, today's lesson is titled Related Rates. This is a big concept in a first-year calculus class. In fact, it's such a big concept that I already told you we'll probably be here the rest of the week on this topic. So this is going to take pretty much everything we've learned and take it to a real-world type application. So here's as close as we can come to a real-world application at the moment. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. Our question is, how fast is the radius of the balloon increasing when the diameter is exactly 50 centimeters? So what kind of things are we looking at here? We got a rate of what? Rate of change of what? The volume of what? Okay, so we've got a rate of change of the volume of the balloon. Is that known or unknown? That's known. Okay. What else are we looking at here? Okay, we're looking at the diameter of the balloon, and related to that, the radius, right? Yeah. Are we just looking at the diameter and the radius, or are we looking at, like we said on the other one, a rate? How fast is the radius increasing? Isn't that a rate? Is that a known or an unknown? So we've got a known rate, we've got an unknown rate. We need to relate those somehow. We've already used the word volume, right? Does anybody have, probably don't have this one memorized, but do you know the volume of a sphere? You can find it very quickly in the inside jacket of your books. I think he's on it. 4/3 pi r cubed. You said pi r cubed over 3? That's right. We're going to need that. We have to start with some equation, right? We have to have some facts, something that we can work on. We have some facts. We have the rate of the volume. That's a fact. That's a known. We have the unknown, the rate of the radius. And we have this other fact that we can find the volume with 4/3 pi r cubed. So this is what we're given. It's really important that you identify what you're given and what you're trying to find. We're given the rate of increase of the volume of the air or of the sphere is 100 cubic meters per second. What we don't know is the rate of increase of the radius at the exact time that the diameter is 50 centimeters. That's what we don't know. That's what we need to find out. So we're going to take another known here and work on this. To rewrite that first given, we are given the rate of change of the volume with respect to time, dV over dt. Does that make sense? The rate of change of the volume with respect to time is 100 cubic centimeters per second. What's the cubic centimeters? That's the volume, right? The seconds is the time. So it's dV over dt. What don't we know? Okay, so can you put that in terms of dV over dt? Actually, it's asking for the radius. dr over dt. Yeah. We don't know dr over dt at the exact moment when the radius is 25. It says when the diameter is 50, the radius is 25 at that point, right? That's what we need to find. So we've got a known, we've got an unknown. And we also have this fact that you guys looked up. The volume of a sphere is equal to 4/3 pi r cubed. Notice in our given, we've got v's and t's. In our unknown, we've got r's and t's. Notice in this function, what have we got? B's and r's. That's really good. We might be able to make something work here. Any ideas on how we could proceed? Just any guesses? Or take the derivative of that. Why? Why would that be a good idea?
That's what we've been doing.
Well, A, that's what we've been doing, and we know dV over dt. That's a derivative, right? That's a rate of change of the volume. So that's a derivative. That's the first derivative of the volume. And we've got a volume here. It'd be cool if we could turn that into a dV over dt so we could use the 100 somewhere. And we can do that if we take the derivative. Same thing with r. We don't care what r is. We care what dr over dt is. So we need to take a derivative somehow. So when we take the derivative, we need to do it to both sides of the equation. We've done this before. It's called what? Implicit differentiation. It's along those same lines, right? Implicit differentiation. So what's the derivative of v? v prime, but we want to do this in terms of t, so we can use these values over here. It's just dv over dt. The derivative of volume with respect to time is dv over dt. Equals, what's the derivative of 4/3 pi r cubed with respect to t? Let's follow the power chain. 3 times 4/3 is 4 times pi. Pi r squared, right? Times, because I'm not doing this with respect to r, I'm doing this with respect to t. So this is the first part, right? 4 pi r squared times, what's the derivative of r with respect to t? There we go, dr over dt. It's the same thing as derivative of v with respect to t is dv over dt, right? The derivative of r with respect to t is dr over dt. Because I've already taken care of the power when I took the 3 times the 4/3. Right, I already took care of that part of the function. And then I dropped that down 1 to 2. Left the r in there, and then I have to follow the chain. I multiply by the derivative of r. And since we're doing this with respect to time, so we can solve the problem, derivative of r, I don't want to just write r prime, like we wrote y prime with implicit all the time. I want to do this with respect to time, so dr over dt. So now I see a dv over dt in this equation. Do I have a value for that? Yeah, it's 100, right? I see an r. Do I have a value for that? I do, because I want to know dr over dt exactly when r is 25 centimeters, right? So I have a value for that. I see a dr over dt, and that's what I want, right? So I basically have 3 variable type things. If I can replace 2 of them, I can solve for the third one and answer the question. So let's do that. dv over dt, you guys told me was 100. I think I solved this for dr over dt before I put the 25 in. I don't know why I did that, but I think that's what I did. So if I isolate dr over dt, I'm going to have to divide 100 by 4 pi r squared. So dr over dt is equal to 100 divided by 4 pi r squared. 100 over 4 is 25. What's r going to be again when I finally plug it in? 25. So I put the 25 in. That's the instant when the diameter is 50, the radius is 25. So if I reduce one of the 25s, the radius is changing at 1 over 25 pi centimeters per second at that very instant in time. And if we wanted to, we could take that to some decimal and round it to some degree of accuracy.